Okay, good evening, everyone. Before we continue, just want to mention that a couple of things. Number one, we I graded homework one, two, literally actually homework one. Homework two I didn't grade, but I already posted the homework solutions for homework one and two. So definitely review them. Majority of the time we don't have time to review those solutions, but in case you have any questions, send me an email and we can discuss. We can also schedule time to discuss offline, or you can stop by in office hours, which usually would be on Thursdays. For example, would be next Thursday, same time slot. So you can dial in and then ask questions. Potentially can be homework questions as well. And then that's number one. Number two, I assume that everyone probably already have the textbook by now, so just keep up with the reading, keep up with the uh, progress in general. And then because now it's still early, only the third week of the semester, so we still have a lot of stuff to go over. So that's number two. And then the number three I want to mention is there's regarding the discussion board. As you have already realized by now, for the discussion, it is graded. Apparently, if you post something, you would get pretty much everyone get full grades. But if you don't post anything, then I think it's kind of unfortunate for you because that way it's pretty much I think it's free. So if you would post, then you would get the grades, and then try to get it in time, so that you wouldn't be penalized by being late. Posting those on the discussion board, and then as I mentioned in one of the emails, when you post in the discussion board, not necessarily you need to start something new. If you reply some others posts, that would also be fine. So in other words, the discussion board is really not to say that you post something. That's really not the purpose. Purpose, of course, you have to do that. The purpose is really that you can read others posts and um, click on the links that other fellow students actually shared, so that you would be able to expand your horizon. Deadline for discussion board. So Valerie was asking what is the deadline for discussion board. Deadline is supposed to be 11:59 p.m. on Sundays, but you probably realized that while I was grading, I realized that some of them is actually 12:59 p.m. Somehow it has 12:59 p.m., which is like 1 p.m. on Sunday afternoon, but I already corrected all of them, so it would be 11:59 on each Sunday. So you won't be penalized as long as you post before that date, at that time. Okay, any other questions so far? You can always feel free to chime in if you want to speak while I speak. And also if you have questions, if you have anything that you would like to discuss, you can either just speak up or just um, uh, post in the chat window. So Valerian was asking, do you have to make appointment for the office hours? No, you don't need to. I would be here from 7:30 to 8:20 every Thursdays, even though I won't stay too long if I don't see anybody online. So if I stay like 20 minutes, no one is there, I will just drop off. So if you, of course, it would be helpful. You think that some of the questions that we're going to discuss is worthwhile to send me an email so that I can take a look beforehand. That will be fine as well. Just send that email, but you don't really need to make an appointment for the office hour. Okay. Any other questions? Valerie, were you here? Were you on the? Were you? I think you dialed in last Thursday, right? And then after a while, I didn't see you anymore. So, uh, you had a question back then, or? But in any case, if you have questions, you can still, send, no question. Okay, you can always, drop by or send me emails. Okay, so, so looks like no one else have any questions, so we can just continue. Um, Hold on, let me pull it out. Mm. Mm. Okay, so now you see my screen. So okay, these are the materials for week 3. So in terms of in general, I feel like it's getting more interesting starting from chapter 4, which would be the material for next week. But we can go through what's happening. Oh, even for the week 3 as well. So so here let's continue with week 3. We talk about what we're trying to cover includes the following. One is fitting models to data graphically, and analytic methods of model fitting, and applying the least square criteria, and also how to choose a best model. So in terms of when we do model fitting, usually it has 3 key elements involved in the model fitting process. The first one is fitting a selected model type or types of to the data. So essentially saying here, essentially saying that once you have the data, you start thinking which model which I should be start thinking about. Is a regression model, is the decision tree model, or is it a simulation model that I should be building? So that's the first thing that you start. So that's why also previously last week I mentioned that even if we have multiple modelers, potentially for the same dataset, same business problems, different modeler could come up with different solutions. And hopefully the different solutions have similar merits and at the end have come up to the same conclusion. That's always the case. That's why there's a famous quote from George Box, who is a statistician. He says, all models are wrong. Some of them are useful. So that's really the case that what we are trying to tell you that you find your data. That's why experience helps, right? Once you have more and more building model experience, you realize, oh, I could do it this way, I could do it that way. What would be the potential pitfalls that I should be trying to avoid, and what would be the stuff that I should be paying attention to in between? So all of these questions you would be able to answer after you have more experience on the data on the modeling side. And then the second question you're trying to do is, you see, choosing the most appropriate model from the competing types that have been fitted. So this is saying that if you tried different models, different methodologies for your data set, which one you should be picking would be considered to be the best one. And then on top of that, once you select a model, you think, okay, this model is really doing better than the rest of the ones. It probably have less assumptions. It probably generate better fit. Could be all kinds of things, right? So that's why you have to select the criteria for comparing on the different model types. And then the third step usually involves making predictions from the selected data. And then the question is also that what type of criteria you should be established for determining how to make predictions, and even you want to measure how effective your model is. That's why usually when we do a model, we have something called in-sample test. You test in a sample, the specific sample in your dataset to see how good that is. And then on top of that, there's something called out-of-sample test. Instead of using the full dataset, you only use 80% of the data, and then use the 80% of data to build that model, and then use the rest of 20% to test your model. And then this type of test is considered as out-of-sample test because you're not building the model using that 20% of data, so that 20% of data is considered to be out of sample. And then the 80% that you use to build your model is considered in sample. So if you test upon that dataset, it's called in sample test. If you test upon extra data that you have, that's called out of sample test. So that's one way to think about how potentially you can validate the model. And then in terms of in the modeling process, you could have formulation error. Could be, the modeler made a mistake and wouldn't be able to come up with the best one. So that's formulation potential error. And also truncation. Of course, I also want to mention for the formulation error, it could be the case you make too many assumptions in your model, too many assumptions that may not hold in the specific dataset. And then next type of error would be truncation error. And what if you truncate data, truncate some of the processes in the whole system or components? Those would be another potential type of error. And then runoff error, if you run up, run down. In majority of the cases, it wouldn't be a big issue. But in some cases, you do need to pay attention to these issues. And then the fourth one would be measurement error. If make sure that your data is valid. Otherwise, any conclusion that we can make from the data will not be valid just because we have measurement error in the dataset. So that's something that some of the key issues that you should pay attention to. And then we also said that visual fitting has potential pitfalls, and the majority of the time we sometimes we do data transformation just because, especially later on we will discuss a little bit on the linear regression. In the case that if the data doesn't quite follow a linear relationship, what if we make certain transformation of the variables that might be able to help to build a simpler model, which would be the linear model that we usually build. And then actually this section I really want to go through a little bit more detail here, and then the key idea here is one of the Chebyshev approximation criteria is modeled as a minimization problem, and it is a linear optimization problem, and it can be solved using simplex method, which will be covered in chapter 7. Even though here in the section we said, I mean that the textbook said they solved it using simplex method, get this solution, so you don't need to worry about that. In case that in the homework you pick this problem for your homework, you don't need to solve them because you don't know how to solve them quite yet to use simplex method. Okay, so let's go to the textbook. So it's in figure 3.2. hold on. Okay, for this particular question, sorry, I was like looking up for figure 3.2. It's really 3.12. Okay, for this one, the question is really that so we have a segment of line segment AC, and then it is divided to two pieces, AB and BC. And then what you want to measure is you want to measure line segment AB, BC, and AC represented in figure 3.12. Assuming that the measurement is AB is 13 and BC is 7 and AC is 19. So you know that there is some sort of error, right? So because you know that AB plus BC should be equal to AC, but apparently it's not. And then in this case, you want to and you should expect in any physical measurement process discrepancy results. In this situation, the value of AB and BC add up to 20 rather than 19. So what we're trying to do is let's resolve this discrepancy of one unit using the Chebyshev criteria. That is, we will assign a values to three segments in each in such a way that with the largest absolute deviation between any corresponding pairs of assigned and observed values minimized. So that's really the idea. So let's take a look at the formulation. So we can use x1 to represent the true value of the length of AB, and then in that case x2 would be BC. Remember that x1 is AB and x2 is BC, so that if we use x1 minus 13, which 13 is a measurement, right? Measurement that we have, so that would be the difference of the actual and the measured value. R1 would be the difference between those two, and then R2 would be the difference between the measurement of BC, the true value minus the measurement of BC, which is 7, and then what's that error term. And then the third one is if the true value is x1 plus x2, in this case we said it's it is a true value, then that's true value, and then our measurement is 19. In this case, the third error term is R3. So what we're trying to do in Chebyshev approximation criteria is that we're trying to minimize absolute value of those, minimize the largest of the three numbers. And then if we see that we set up that, okay, if R1, let's look at the first constraint first. Subject to the three conditions, the first condition is R1 absolute value less than or equal to R. And then meaning that R is the largest among those three if you look at the three equations, right? R is the largest of the three numbers, which is the absolute value of those three numbers. What we're trying to do in terms of objective is we're trying to minimize this R. So we set up this relationship, which is the Chebyshev approximation criteria that which is covered actually in the previous section. I hope you already read that. That's the whole point I was trying to see, that if you haven't read the textbook, you wouldn't gain as much as you could. So so if we go to next slide, next piece, that the question is, what if we instead using this R1 absolute value less than or equal to R, we can replace that relationship by two linear equations. That is, you can assume that R1 is larger than or equal to 0, what you get, and then R1 less than or equal to 0, what you get. And then based on those two relationships, you can use those two based on those two potential possibilities in terms of R1 larger than or equal to 0 or R1. No, sorry. R1 is the true value would always be larger than or equal to 0, right? So R1 absolute value less than or equal to R would be equivalent to R1 larger than or equal to negative R less than or equal to R. In that case, if you rearrange those two larger than equal to or less than equal to relationship, you would come up with this these two equations. That's clear, right? And then based on these two, so if we do it that way, we say, okay, let's use those to replace those two inequalities, and then try to go back to the previous relationship, so that previous formulation, so that you would be able to represent previous program into this linear program. And then this problem is called a linear program just because apparently we can see that the objective function is a linear program and all the constraints are linear program. So now this is more like a 300 view of what is a linear program. So in that sense that linear programming is trying to have a certain objective function with a lot of constraints that have to be satisfied. In this case, right, you minimize that R subject to all these relationship. You think about in applications, in many of the cases, for example, a company want to make certain investment and then they want to maximize the expected return constraint on you have a budget constraint, right? I have $300. I cannot spend all my $300 on food. I probably spend 1/3 of on food, and then so that you say, okay, I can buy X, I can buy Y, I can buy Z. They are all food, but X1 plus Y1 plus Z1 plus and also certain units of those different goods has to be less than or equal to $100, right? In that case, that would be one constraint, and also you can add some other constraints in reality. So in any type of a decision like maximize or minimize type of problems, you can use optimization. I just made up an example like the one that you want to minimize your investment return, maximize your investment return. And also some other like transportation companies minimize the total cost that the travelers experience, in the sense that total travel time or total travel cost. So that's all type of problems that is out there that you can use methodology for linear program. So and then for now, you just remember that you can use simplex method and to solve this problem, and here is a solution. So with that being said, this is really a nutshell of okay, we have certain objective, we have certain criteria that we can pick. In this case, we're trying to minimize this largest absolute value of all, and then we translate them into a program, linear program that can be solved. One of the homework is actually using very similar methodology, so that just to give you a sense on this. And then if we follow through here, right, another example here says minimizing the sum of the absolute deviations. So that's another possibility, right? So previously in the slides I just mentioned, you need to pick up a criteria. In this case, we're trying to minimize certain things as well. You can formulate this way, and then you try to optimize your solution. And in this case, another question here, least square criteria. And then if you are familiar with linear regression, if not, that's good. You should learn this, right? You would know that what we're trying to do is in linear regression, what we're trying to do is we're trying to find the function form of xxi. Yi is really the actual value that you in your data, but you're trying to find the function form of xxi. So in linear regression, what you're really trying to do is trying to minimize this least square of the measurement measure and the function form that you are trying to fit. That's another reason that we always call linear regression as least squared regression. So let's continue with the slide based on here, since it's a good point that we go back to the slide. So as I briefly mentioned here, least square criteria is for regression, and then let's say continue, right? And then here fitting a straight line is an introduction to linear regression. So what we do is formulate the least squares and then let's actually have to go back there. So what you do is remember that in order to, in high school mathematics, right, in order to minimize a quadratic function, what we just saw there, least square objective function, least square is quadratic, right? In order to find a minimization value of that function, what you do is take partial derivatives, and then you set partial derivatives to 0, solve for slope and intercept, so that you get the best A and B. So it's a little bit abstract, so we need to go back here and okay. So here is what I'm saying, right? So what we're trying to do in linear regression, what we're trying to do is we're trying to find a model which is y equal to ax plus b. That's a straight line, right? B is the intercept, A is the slope. And then we are trying to find this function form. Essentially, we are trying to find A and B so that we want to minimize this S. S is actual value minus the fitted value from the A and B. And then in order to find the quadratic function minimal value, what you do, as I mentioned here, you take the partial order derivative in terms of A to set up the first equation, and take the partial derivative of B, set up the second equation, so that you have those two equations to be solved, and you have two unknowns, which it would be the A and B, so that you would, based on continue with those two equations, you come up with 3.5 and 3.6 being the slope and intercept, which is the A and B. So that is saying that linear regression itself is a optimization problem. The function form of the objective function is a quadratic function, right? So it's nonlinear. It is really a nonlinear function that's there. And then if we continue with this idea, if instead of fitting a linear line, what if we fit a power curve? And then it's even continue. It would be nonlinear regression in the sense that you have power curve there. You could always have multiple x instead of just x powered by n. You could have x1 powered by n plus x2 powered by m plus x3 powered by b, for example, right? You can always have all kinds of curves that you can solve. And then similar approach that you can see here, still partial order derivative trying to figure out the slope A in this case, right? Okay, with that being said, that's pretty much that we are trying to cover actually for this section. Let's continue. And then potentially we can transform least squares fit transformation from nonlinear to linear. And that's you can read through that part as well. But that's really what we're trying to do. And the question now becomes, how can we choose the best model? We already at the beginning we discussed 3 steps, 3 key elements that we need to think about. And then here, one of the things here we can do is look at the fitting error, comparing the different models and see which error which fitting error is the least. And even last time in one of the homework we said, okay, look at the error term versus the observation number, and then whether they're random. That's really one of the key assumptions for linear regression. If you read deeper in some of the linear regression material, you would realize that what we are seeking here is that error term should be normally distributed with a mean of 0 and the sigma square as the variance. So in that case, that essentially says the error term should be really random. It can be small, can be large, but it's hovered around 0, sometimes -1, sometimes -2, sometimes positive 0.5, sometimes positive 1, etc., etc. So there's any type of pattern or trend that you would be able to observe from the error term, which we are actually going to cover in some later sections as well. So for now, at least you know what I'm kind of talking, why we are trying to find all these terms. And then the considerations could be error, this one. Second one would be complexity of the model, how complex your model is. Not necessarily more complex, the better, right? Especially in business settings, you don't really want to find too complex of the model just because data collection would be an issue. And also once you have too many dependencies on different components, you just don't know if the model would still be working as it's supposed to, especially the data quality issues as I just mentioned. And next thing is the overfitting of the model. I'm sure you already studied, studying computational mathematics. You don't want to overfit a model. You really want to have good balance between the variance and the bias and variance that we talked about, right? So because of the capability of the model that's not overfitting the data, then you would be able to think about generalization of the model. So all of these have been touched upon in the textbook. Apparently, you should pay attention to. Definitely read them through. Okay, here is a homework for this section, and continue with next section. This is the still chapter week 3 material because we don't really have a lot of material for this chapter. It's more like examples and the applications of chapter 3. So here, let's continue. So here we specifically try to give you the idea of overfitting. Apparently, you already know that B is a better model than C just because C is kind of overfitting. I just want to mention that I believe one of you actually in one of the homeworks did exactly the same thing, try to connect all the point and say this is a model. That's not the way it should be, right? If you already studied computational mathematics, you shouldn't come up with that type of model just because we know C is overfitting the data. What is overfitting? It doesn't have any generalizability, and then it literally fits every single point of the data. So that's that. Okay. Oh, by the way, I know that some of you actually are taking these two courses simultaneously, but I don't think it would be a big issue. So just continue along, and we should be fine. And then another thing here I want to mention is sometimes you would think about transforming some of the models into linear model. For example, if you find a relationship that instead of ax plus b has a relationship, you find that y is really dependent on z squared instead of z itself. So in that case, you can transform z squared to be a new variable x, for example. Then you conserved the linear relationship between a and x instead of a z squared, right? So in the textbook specifically says, okay, majority of the time you could consider in ladder of powers, consider this sequence of the transformation if you want to transform certain of the model form to a linear model. Okay, continue along, and then textbook talked about, what if you do different ways of transformation, how would that affect your results? Okay, we really don't have time to go through really some of this detail of this, but pretty much here I want to mention here is For lower order of polynomials, means x powered by 3, and higher order of polynomials would be x powered by 7 plus x something x powered by 6 plus etc., right? So, and then what we can see that if you have multiple observations, once you fit the model with higher order polynomials, you know you probably can fit the data better. Once you fit the data better, you know potentially you could overfit the data, right? So so here, if we think the other way around, if we use lower order of polynomials, the error can be worse just because you don't fit the data as well. So if you think about this graph, then B has worse error than C, right? If you think about picture wiggly woggly points, then you fit all of them, literally every single point, then your error is really great. But if it's a lower order of polynomial, your error can be worse. But the complexity of the model decreased, right? It's lower order, it's easier to fit. You don't have so many terms to fit, so many coefficients to think about to make a decision on. And then the third thing is overfitting of the model decreased because less chance you would overfit the data. And then, but on the other end, generalization of the model actually increased for a lower order of polynomial, right? This all makes sense. And on the other end, higher order of polynomials would be opposite to what we have for this. And then specifically we want to introduce here is something we call it linear splines, also called piecewise linear functions. So what in many of the analysis, you know, in business setting, for example, you think that instead of a straight line, you know it would be two segments. You know, okay, from x1 to x2, certain range of certain aspect of business, it has this relationship, but from x2 to x3, it has a different function form. It just have a higher, quicker, higher slope that make the y value increase much faster. So that's something we call it linear splines. And then what is a cubic splines would be the second chart. It's trying to say, okay, it's a cubic function with a quadratic term and a linear term as well. That is the cubic splines. Okay, here introduce you these two functions, you know, two potential model forms. Read through the textbook for this section as well. Okay, so that's pretty much that we have for this week, but remember that we also need to cover the material for next week. And then these are this week's homework, saying that you can pick 3 out of chapter 4 and chapter 3 and chapter 4, ideally 2 from chapter 3 or 2 from chapter 4 and 1 from the other chapter, so that you have at least 3 questions that you can work with. That's the homework for this week. Let's continue for next week because okay, so in this section we're trying to introduce simulation modeling. I know that there is a separate course on simulation, so I'm sure that you'll cover much more detail on this. Prior to the simulation course was developed, we were kind of designing the curriculums in the sense that there is no single simulation course, and then we are using this chapter to serve as an introduction to simulation. So so in this section, there are 3 major methods. Number 1, simulated deterministic behavior area under a curve. Number 2, generate a random number. Number 3, simulating probabilistic behavior. And 4 and 5 are really applications of 1, 2, 3. Of course, 5 Turing models itself is not quite simulation. It's really Markov chain related. I have some links and YouTube's that I find interesting, worthwhile reading through. I post them in the section in the week 4 material, so you should read them through. And then you would realize in certain cases you use queuing model, but in certain other cases you use simulation model, which goes back to last week discussion that 2 weeks ago, the discussion that in what case you use a math model, in what case you look at the real actual world data, in what case you actually build a simulation model, right? So going to next section, rationale for using simulation models. We're not able to construct an analytical model adequately explaining the behavior observed, and use simulation to obtain data needed for further analysis as a potential another possibility. The third possibility would be alternative procedures need to be tested may not exist. So other than simulation, you have no other choice. And then question becomes, for simulation, you know behavior itself can be deterministic, can be probabilistic. The model can be simplified version of probabilistic, become a deterministic, can be from deterministic we can go to probabilistic to construct a model. And then in terms of simulating deterministic behavior area on the curve, the idea is simple. What we have is we have this curve, right? You know, in college maths, you can do college calculus, you can do integration to get that area. But here we're saying that instead of doing that, let's do simulation. What we do is, if you look at the equation on the top right, area under curve divided by area of the triangle should be equal to number of points counted below curve divided by total number of random points, right? If you just generate a number which has the x coordinate and y, you generate a pair of numbers which would be a x and a y, and then you, based on that x value and y value, you know where that is. For example, this p on the curve. P is under the curve, right? If it's under the curve, you increment your counter, the counter for number of points below the curve, then you increment that. If it's not under the curve, you don't increment, but you increment the total number of the throw, total number of random points. So you have two different counters, and then at the end, you use the first counter that's under the curve divided by the total number of throw. Then you can get the area under the curve, right? That idea is simple. So that if you look at this, all these input, output, etc. algorithm essentially is what I just described. Okay, so let's continue. For here, instead of 2D, what we say, okay, what's the area under a 3D surface? Idea is actually the same. Instead, generate two-dimensional in a 2D space, you generate, instead of generate two numbers in the 2D space, you generate three numbers from the 3D space, so that you have x, y, z. In step 3, you have x, y, z, which is between 0 and 1, and then in certain cases you increment that counter in step 5, otherwise you don't increase your counter, and then n is really the total number of points that you try to generate. Okay, and the next section we're discussing here is how to generate a random number. Majority of the time we have three methods. Remember that it's not only the three, there are multiple other pseudo random number generators that people are trying to research. And then, here we actually introduced two of them. So let's say the first one is middle square method. Start with a 4-digit number. X0, you call it as a seed, starting with that point. That point is always considered as a seed. And square it to obtain an 8-digit number, add a leading 0 if necessary. If you only have 4 numbers, then you add 4 zeros in the front, and then you take the middle 4 digits as the next random number. That's how you generate a sequence of the random numbers. One method, method one. Method two is called linear congruence. What you do is you have a modulus function, and C is a modulus, A is a multiplier, and B is an increment. And then once you pick a x0, you will be able to find your x1, x2, x3, etc., etc., and then use these numbers as your random number. And then pay attention to possibility of cycling, lack of statistically independent among numbers in the list of random numbers. That's a key reason that in simulation we call this as pseudo-random numbers, because they're not random. At the end, they do have some relationship, and usually it could potentially cycle. And then we do have homework that help you to understand these concepts better. Okay, and next question. How can we model a probabilistic behavior? Suppose that we flip a coin, and then we roll a fair die, and what's the probability we get a for a fair die? What's the probability you get a 1, right? Theoretically, we all know it's 1/6. But the reality is, if you roll it 600 times, apparently you want to get 100 times. That's how the whole thing of probability, right? So the thing is becoming more interesting. What if it's not fair? It's not a fair die. What can you do? How can you get the probability that you can get a 1 in the continuous 600 throws, right? That's the whole purpose of simulating probabilistic behavior. So let's look at one of the example here. This example is a fair coin. We say that total numbers input is total number of n random flips of a fair coin to be generated in the simulation, and output is the probability of getting a head when we flip a coin. So the idea is also simple, right? When you flip step 3, you get a random number between 0 and 1. If it's between 0 and 0.5, then you say it's a head. You increment that counter of head. Otherwise, you just don't do anything. At the end, in step 5, you calculate that probability of head equal to counter divided by total number of throws, which is n. That's a fair coin. And then fair dice, very similar. Once you generate a random number, you think about whether it's between 0 or 1/6. Otherwise, you just increment different counters and then use different counter to divide it by the total number of n, and then get your probability of each segment. What if it's unfair? In the sense that, as you can see here, x3, the third row says x3 has a higher probability between 0.2 and 0.4 instead of 1/6, right? So in that case, you just generate a random number to check which category it belongs to and increment the corresponding counter. Apparently, you already know how you define the unfairness of that die in this case, right? So that helps you to get that probability. This is another way to look at how to use simulation to generate those, to simulate these probabilistic behavior. Okay, that's actually pretty much that I would like to cover. And then 5.4 essentially is a application of what we just discussed. It's a more complicated situation that you have more things to consider when you try to think about inventory cost, delivery cost, and demand cost. This is a classic example question that's facing a lot of consumer products, supermarkets, for example, and e-business, Amazon, for example. They do face all these problems. Apparently, you can use mathematics to solve it. You can use simulation to solve it. And then queuing models, as I mentioned, review the slide, the material that's posted in week 4. How can we use queuing models to to analyze the checkout counter efficiency, for example, right? And then we could also potentially use simulation to look at the checkout counter efficiency. That's the reason we introduced queuing models in this section. It's really smaller section that it's like Markov chain itself is way beyond what we can cover in this section, but it's worthwhile to read through. Of course, you can model morning rush hours, you can model multiple server queues. This can be used in supermarkets to estimate how many servers checkout booths might be needed for queue models. That's the homework for next week, and that's pretty much that I plan to cover for these 2 weeks. I hope that you enjoy the reading, you go through everything, and try to understand the concepts. These could be very helpful when you actually apply them. Okay, any other questions before I go? Nope. So if you don't have any question, I can just stop here. And again, next week at 7:30, I should be around to answer questions if you have any. And also feel free to send an email anytime. Don't forget to post on the discussion board every week. It's free. Again, it's free for you. So, okay, that's it. Nice talking to you guys, and talk soon. Have a good night.